Hello, welcome to I Can Science That. Today we're going to talk a little bit about friction. I have a request from a viewer. The viewer has very politely requested that I look at this particular thought experiment and answer some questions that he has about that. And so that's what we're going to do today. Let's talk about the thought experiment. What we have is a block, a mass, that we are going to slide along a surface. Actually, in the original thought experiment, we were going to roll the mass, but I would prefer to use sliding. I hope that's okay. Sliding is less complex than rolling because there's no rotation involved. We don't have to talk about whether there's any kind of fancy expressions that we need to do if objects are rotating. So let's just do the sliding. This is a thought experiment, but it is something that you could absolutely do at home. You could do what I like to call the dollar store physics. You can just get an object, a nice smooth surface, some kind of hard object. Like don't use rubber or anything too sticky. Probably like a metal thing, and then slide it along the floor. And then your goal would be to measure what is the position of the object over time as it slides and as it eventually comes to rest. So you'll slide the object and then you just need to measure those positions over time. And I think a really good way to do that might be to just film it. If you lay out marks along the sliding surface of distance marks along there, or put a measuring tape down along the sliding surface and then simply film the thing sliding. You should then be able to go back through the recorded video frame by frame and mark down the position of the sliding object at every time interval. And then you can create a graph of the position of the object as it was sliding. And from there, work out the velocities of the object at different time intervals. And you can work out the accelerations that you were seeing over those different time intervals. And I think it would be very easy to do and might be kind of fun if anyone's interested. So let's take on your thought experiment. We're only going to do it in digital form. We're not going to do it in meat space today, but this is what you've put forth. The second mass is the same mass as the first. So I have my yellow mass and my blue mass, and I'm going to say, let's make this easy, 1 kilogram each. Alrighty. And, maybe I'm using a spring to shoot them, or you could just flick it. Like if you're just doing this on your own, you don't need them to be a particular velocity in order to take these measurements. You could do any velocity you want. And so just flicking the thing could give you data that's just fine. But you have specified that the first one is going 1V and the second is going 2V. So let's give those some units. We'll call them 1 meter per second and 2 meters per second. So we're going to launch these guys. We launched the blue one at 1 meter per second. We launched the yellow one at 2 meters per second. And what's going to happen? Boom! We'll see that because the yellow one is going faster, it goes farther. And there's no controversy there. We're all on board there. And also, it took longer to stop. I think you'll notice that it starts off faster. It's going to go for longer and it's going to go farther. Okay, sweet. That's our setup. You have mentioned the first one travels 1 distance, the second travels 4 distance. And I would agree with, conventional physics suggests that's probably going to be a good approximation of how far they go. If you give it twice the speed at launch, it actually goes 4 times the distance when sliding. And we did see that they traveled for different amounts of time. So what are those times? We're going to need that. If the yellow one starts off with twice the speed, right? Starts off with twice the speed of the blue, it will take twice as long to come to a stop. If we're expecting constant deceleration, constant acceleration here, it will take twice as long to lose 2 meters per second as it takes to lose 1 meter per second. So In our thought experiment, the blue object takes 2 seconds to come to rest, and the yellow object takes 4 seconds to come to rest. All right, so here comes the question. That's the setup. Here's the question. You would need to explain how it has 4 times the energy in this circumstance when the first travels 1 distance, the second travels 4 distance. Okay, the key word here, the vocabulary word is energy. I want 4 times the energy. So in order to quantify the energy, I need to know what exactly the energy is so that I can put a number to it. We need some definitions. So I'm going to use contemporary physics definitions in the context of a high school physics classroom. That's what I want to, that's about the level of discussion I think is appropriate right now. So if you're, just starting in high school and you're taking your first physics class, they would need to define what is energy so that we can use that word and everyone knows what that word is supposed to mean. So I'm going to suggest a website for that instead of a literal textbook. Let's go to a website targeted at that level. And I found one that I think works called BYJU. So let's go and look at that. Okay, here we are at byju's.com. And the definition is given for energy. Energy is the ability to do work. Okay. This leaves us with an obvious problem, which is, what is work? I can't define energy in terms of work unless I know what work is. So let's go and look up work. Okay, here we are. Work is the product of the component of the force in the direction of the displacement and the magnitude of this displacement. Kind of a mouthful. Here's the mathematical expression right here. That part, we'll look at that part. That's the mathematical expression. What are we saying? We're saying an object is moving over some distance. So that'll be d. I think we don't need a definition for distance. I think we're all on the same board, same place there. And then we want to take the amount of displacement, right? That's the distance the object moved, and multiply, product means multiply, by the component of the force in the direction of the displacement. So that's this. This is, you're pushing on an object with some force, and whatever amount of that force is pointing in the same direction that the object is moving, that's the amount of force that we put into this equation. So that's what that cosine theta there is. So, but in our example, that's going to simplify. But if we're going to define work in terms of this thing called force, we need a definition for force. So here's force. Force is the push or pull on an object with mass causes it to change its velocity. Okay, so what are we going to need? We're going to need a push or a pull of some kind, and it has to be on something with mass, and that mass has to change its velocity. What we're going to do then is we're going to say that if we observe a mass, and that mass is changing its velocity, then we are observing a force, because that's the definition of a force that we've got here. The definition of a force, and there's a few of these, they don't all line up, but let's use this one for our discussions. The definition of a force says that if a mass is changing its velocity, we are seeing a force. We're going to need to know exactly how much force. So in order to quantify that, to put a number to it, we will use this equation, F equals ma. And where do we get that equation from? That is Newton's second law. However, it should be stated that is not how Newton wrote his second law originally. This is the contemporary writing of Newton's second law. It has the same meaning that Newton originally discussed, but this is using our nomenclature, the nomenclature that we're going through right now. So this is essentially the translation of Newton's original text into modern contemporary physics classroom. Okay, so we're going to need to know, if we're going to do this, force, We need one more definition. I'm going to assume we know what mass is. We've been using mass already. You gave me some masses, so I'm going to consider that one done. Acceleration. We're going to need a definition of acceleration. So here we are. Definition of acceleration: the rate of change of velocity with respect to time. All that means is you take however much your velocity changed, divide by how long it took to make that change, and that is the quantity we are defining to be acceleration. Energy is defined as the ability to do work. Work is defined as essentially this equation, the amount of force you are pushing with in the direction the thing is moving, and multiplied by how far you got it to move. This is the definition of work. And work is defined to be energy. Energy is defined to be work. Work is defined to be this equation. And then we had force. Force is the push or pull on a mass causing it to change its velocity. F equals ma, where acceleration, acceleration is defined as the rate of change of velocity with respect to time. So if an object with mass is changing its velocity, we are observing what we call a force. That is what is called a force. And we can measure the amount of force using the acceleration. The acceleration is just how much did the velocity change divided by how long it took to make that change. And that will give us the amount of force. Based on the amount of force and the distance the object moved, we are observing this quantity that we call work. And I will ask you to be patient and understand that I worded that way on purpose, that this is that we are observing an effect that we call work. What does it mean in physical reality beyond just that I called it work? At this point, nothing. This is all that it means. All I want to do is establish a common vocabulary so that we can speak clearly and precisely and not make any mistakes because we're discussing things vaguely or thinking intuitively. We're going to be very precise and careful. Nothing in any of this that I've gone over is dogma. None of it is in any way even a description of the universe. This is the definitions of words. That's all this is. This is a vocabulary of words. We have these 4 words: acceleration, force, work, energy. And those words have particular meanings, and they're given mathematical expressions so that we can be precise and quantify exactly what the number is, so we can write that number down. And we are making no claims that there are relationships beyond the definitions. Nothing about what happens in the world. I have made no claim of how energy is related to heat. I have made no claim about how energy is related to electrical power or anything of that nature. I'm working only from the definition that energy is work. And I'm doing that so that we don't argue about that. We're just going to agree that that's what the word means. So with that, what the word means, I am now going to literally answer your question. And I'm going to start with acceleration. The acceleration is the rate of change of velocity with respect to time. So the delta V over the delta T. What is the delta V? What is the delta T? The objects in question, this first one, started with 1 meter per second, and it took 2 seconds to come to a stop. So its delta V is 1. It went from 1 meter per second down to 0, so it changed 1 meter per second. And how long did it take to do that? It took 2 seconds to come to a stop. That is 0.5 meters per second squared. And we don't have to, hopefully we don't have to get tripped up about this square there. Just like it's written here, that just means meters per second every second. So for every second it was sliding, it lost 0.5 meters per second. That's what this says here. and it was sliding for 2 seconds. So in the first second, it lost 0.5. In the second second, it lost another 0.5. And so it took 2 seconds to run out of speed. Right? That's what that says right there. Let's do the yellow one. Yellow one starts at 2 meters per second, and it slides for 4 seconds. So let's plug that in. 2 meters per second divided by 4 seconds is also 0.5 meters per second squared, meaning the yellow object is losing half a meter per second for every second that it slides. So this is half a meter per second for every second. That's what that notation indicates. And it was sliding for 4 seconds. So in 4 seconds, we've used up all of our 2 meters per second. Okay, there's our accelerations. The acceleration together with the mass allows me to get the force. And I've written here force of friction. We're presuming that the reason that the objects stopped sliding was that they were experiencing friction with the sliding surface. It's a thought experiment, so we are discounting any other source of potential force. I'm calling it friction, and we're presuming that it's a constant rate. Really, what we've observed here is just the average force acting on the object as it was sliding over the period of time that it was sliding. We can't actually say for sure with the data that we have that it was acting at a constant amount of force over that entire period of time, and we can't say that all that force came strictly from friction. But what we did was we observed the object changing its speed. We observed the change in speed, that's right there, and we will quantify the amount of force that means through this equation. Here we go, those are our numbers. Plugging them in. The blue object has 1 kilogram of mass, and we observed 0.5 meters per second squared of acceleration. That is 0.5 newtons. And if you're doing dimensional analysis with me, that is actually a kilogram meter per second squared. That's shorthand for that mouthful is the newton. A newton is a kilogram meter per second squared. Okay, so let's do the yellow guy. How much force is the yellow one experiencing? 1 kilogram, half a meter per second, also 0.5 newtons. Okay, it is worth pausing right now to stress that we observed the same amount of force, the same average force acting on both objects, but they acted for different amounts of time. I'll remind you, the blue one was experiencing half a newton of force for 2 seconds. That's what we witnessed. The yellow one, we observed half a newton of force acting for 4 seconds. That's what we saw. So getting that towards energy, the definition of energy was the ability to do work. So how much work do we have? What was work? Work was this equation, and that cosine theta. In our case, the force is what we're observing. We're observing the net force. If there's any other forces acting that did not cause the object to move, we're discounting those by virtue of how we're measuring our force. So that means the angle will be 0, and the cosine of 0 is 1. So we have this very simple expression for how much work was done in this example. So let's just plug in our numbers. We have our forces, we have our distances. Let's plug those in. The blue object we observed half a newton, and we observed that it moved 1 meter. So that's 1/2 of a Newton meter. A Newton meter is also called a joule. Usually you stick with Newton meters because it's not that much of a mouthful, but you could call that a joule if you want. The yellow one was also experiencing half a Newton, but we measured it move 4 meters. So multiply those out, we got 2 Newton meters. What is the point of all this? Energy was defined to be the capacity to do work. Work was defined by this equation. We worked it out, quantified it. The numbers say the amount of work for the yellow object was 4 times the amount of work of the blue object. And this was your question. Explain how it is that it has 4 times of energy. Well, honestly, the reason it has 4 times the energy is because that is how energy is defined. We measured that they have the same mass, 1 kilogram. We measured their starting velocities at 1 meter per second and 2 meter per second. Energy is the ability to do work, so we need to apply the equation for work. We did those equations, worked through them, and quantified how much work that is. It's half a Newton meter for the blue object, and it's 2 Newton meters for the yellow object. That is a ratio of 4 to 1. And so why is that? It's because that's the definition of energy in physics class. I believe that you're trying to say, what is this 4 times energy good for? Can I do work? Is work useful? Can I do something to show that I get 4 times the result in some way other than just this math? The math says I can do 4 times the work, whatever work is. But what does it mean to me, like in a practical sense, right? I think that's what you're trying to get to. It seems kind of unintuitive that starting the block with twice as much velocity would have 4 times the much of something meaningful. But let me put it to you this way. What is something meaningful? What does that even mean? We have this definition for work, and we could discuss and debate whether this form of work is meaningful. But you said yourself the object moves 4 times the distance. Is that not meaningful? It seems like there's a point of view, at least, where this 4 times distance was useful. If my job, my work is to move the blocks, right? That's my whole job, and that's the work I'm trying to do, is to move these blocks. We try to move the blocks, you give it 1 meter per second, and it moves 1 meter distance. If I give it 2 meters per second, only twice as much speed, I got 4 times of my work done, if that is my work, right? So I think what we'll want to do, what I want to do with this is come to an understanding with the vocabulary, and then try to have meaningful discussions about what is useful about this thing we call work, if anything. It could be that it's just a silly mathematical thing that we're just using, okay? All right, so here was the next part of that same first question. It says KE versus MV. Momentum is really energy, while kinetic energy isn't. That's the crucial point. We have definitions for energy using work. We do not have a definition yet for momentum. Here is the definition of momentum, and you stated it right there in your question, so I know you know what it is. It is defined as the product of an object's mass and velocity. That's couldn't be simpler. It's just mass times velocity, and we'll write it with a P. P for momentum. This episode is brought to you by the letter P. So P for momentum is just the mass times the velocity. And we'll just put this in our table of vocabulary. You knew this one, but we'll just put it on there for completion. And I want to put it on there for comparison, because you had said that kinetic energy is momentum. And I'm saying, well, it doesn't look like it. At first glance here, I have very different sounding descriptions of these two things, and the equations that I'm given make it pretty clear what exactly we're trying to get here, and they don't look the same. So, reminding you, the definitions that we got from BYJU's. So this is a typical contemporary physics high school classroom definition. And I'll say it again, this is nothing in these 3 statements is making a claim about how the universe works. It's not making a claim that work is useful as a quantity. This is just telling us what that quantity is. So ideally, there would be no skepticism about these definitions. If you want to look in other texts to find alternate definitions, I'm open to that. Right? We could find alternate definitions. They'll be close to this if we're looking at a contemporary high school level textbook. So let's look at the momentum then. Let's investigate the momentum question and compare that to the energy that we've already calculated. So here we are. Momentum is just mass times velocity. Let's fling our guys. The first one, the blue one, has 1 kilogram of mass. It starts at 1 meter per second. So that's 1 kilogram meter per second. And using that same relationship I said earlier, where a kilogram meter per second squared is a Newton, that means a kilogram meter per second is a Newton second. So I'm going to use this little shorthand, Newton seconds, for the units of momentum. Our blue object launches with 1 Newton second of momentum, and then as it slides, it's losing its momentum. It's giving its momentum to the sliding surface, and it's giving it away. It's losing its momentum as it goes, and it eventually comes to a stop. The yellow object starts with 2 meters per second. So it's got 2 kilogram meters per second of momentum, or 2 Newton seconds of momentum. It has twice as much momentum, and the floor is scraping that away at the same rate. So it takes twice as long for all that momentum to go away. Cool. Let's summarize in a big old table here. Here's all the data that we looked at for these two examples in our thought experiment. We have the same mass for both shots. We have twice the velocity, 2 times the velocity, and that led to the object sliding twice as long, took twice as long to come to a stop. But it managed to cover 4 times the distance in that period of time. The accelerations we observed during that time was the same. It's just that the acceleration acted over a longer period of time in this case, right? So the accelerations and thus the force we observed was the same during that period of time. But here's really the question. The work and the momentum. The work and the momentum are right here. The doubling the speed of the object doubled its momentum. But doubling the speed of the object seems to have quadrupled the amount of work that we did. And why is that? Because of the way work is defined, right? I say it a million times here. I'm not trying to claim that work is conserved, that any kind of relationship to anything in the real world outside this number has any meaning at this time. I just want to agree that we did observe 4 times the work by applying twice the momentum to the object. And that should immediately trigger you to be perhaps puzzled. It doesn't seem immediately intuitive, but let's look back up on the chart here just a moment and see that it took the object twice as long. This is the time column. It took twice as long to come to a stop because it had twice the momentum. But it traveled 4 times the distance. Thus, we said it did 4 times the work. This is the exact relationship that we're looking at. The relationship between momentum and force. Here's the force scalar. This is time. Momentum is a force acting for some period of time. So if we doubled the time, we doubled the momentum. Energy, though, energy is in units of Newton's meters. So it's a force acting over a distance. So if we could quadrupled the distance, we quadrupled the work. That is how it goes. And if you don't like this, saying, oh, I don't like this work unit, you still have this distance unit. That was something you gave me in your original problem, your original formulation of the problem. You had the distance was 4 times as much. If we're making up our own definition of what does it mean to do work, I think it would be reasonable to imagine we could suggest that the amount of distance we moved an object is relevant to how much work we did in the situation, right? If you moved your object 1 unit and I moved my object 4 units, did I do 4 times the practical work? I think that's a discussion we can have now. But for now, I just want to stress that these are just numbers, and they are just quantities that we have defined to be this way. And so if it puzzles you that an object can do 4 times the work when it's only twice the momentum, I'll say that is because of the way we define the word work. Work and momentum have specific definitions, and they're just not the same definition. And at this point, it's been 30 minutes already, so let's stick a pin in this one. We'll come back with a part 2. The call to action, dear viewer, the follow-up for this part 1 video is to acknowledge or discuss the definitions that I demonstrated and whether my quantities do match that definition. Let's launch off from this video, and if we agree to the vocabulary, we can then start the conversation about theories of how the universe really does work and how we can develop experiments to test that. Okay, see you in the next one.